Hello and welcome to the first of our electrostatics videos. This is all about charges and electric fields. So there are two kinds of charge in the universe. Where do they come from? Well, you might be familiar with some of this. Negative charges are mainly mainly come in the form of electrons. Now, there are other things in the universe that are negatively charged, but we will mostly be dealing with electrons. Electrons have a charge of -1, sort of. And one of the important things about electrons is that, as you might know from chemistry, these are the things that are free to move around within materials. They can form electric currents, they can hop from one atom to another, they can be shared, all kinds of things like that. Electrons like to move around. Positive charges, on the other hand, are only found in protons. Again, there's other things that are positively charged, but we're mostly going to stick with protons. They have a charge of +1, sort of. And they are tightly bound within the nuclei. So unless they're just like floating in free space, some positively charged object floating in free space, when they're part of a desk or your shirt or a bicycle or whatever, they can't move. They're stuck tight in the nucleus. So if something is positively charged, it's usually because there's too few electrons on it, not because there's too many new positive charges. When I said that they sort of have a +1, -1 kind of thing going on, um, that's because in physics, we don't measure it in the same way in chemistry. In chemistry, you've got pluses and minuses, right? You've got Na plus and Cl minus. In physics, though, we don't want to count individual electrons as +1 or -1 because we have far too many electrons to do that. And so the unit of charge that was adopted well before we had any idea of what an electron was is the coulomb by our French friend, Mr. Coulomb here. And it's defined such that the charge E, the fundamental charge of one proton or electron, is equal to a very small number, 1.602 times 10 to the -19th coulombs. So that means that if you have 1 coulomb of charge, that's actually a lot of charge. It's like 10 to the 18th individual little electrons. And one individual proton or electron has a very small number of coulombs of charge. So this is how we're going to do it. So if you ever see a proton or an electron in a problem, that's the charge on it. Where might you find that number, you ask? Well, it's on your formula sheet, on the AP Physics formula sheet, right on the first page of physical constants and stuff. So we've got these charges, plus and minus, and they're all measured in coulomb. You might be aware from other physics classes or from something else that if I have like charges, like 2 pluses or 2 minuses, they want to repel each other, they want to run away. But if I have opposites, it is Valentine's Day when I'm recording this, so if you have opposites, they love to attract each other. And the question is, why that thing? Well, our first perspective that we want to take is that charges move because of electric fields. So if you want to know how a charge will move, you need to know what the electric field looks like. So what do I mean by that? Well, let's imagine that I have an electric field like I have here. So these black lines represent my electric field. So you can see here that I've got an electric field that's pointing to the right with some strength E. And I want to be able to calculate the force on some charges. I've taken a positive charge and a negative charge out of my pocket and placed them down here in the electric field, and I don't want to know what's going to happen. Well, we have this formula. This happens to be called, this is part of what's called the Lorentz force, if you're interested in that, which is F equals QE. So in this case, if I want to know the force, it's equal to the charge times the electric field. Well, notice that this is a vector equation, and what that means is if I have a positive charge, my force is actually parallel to the electric field. It moves, my positive charge will get pushed to the right with a force of magnitude QE. If I have a negative charge, now it's still going to have a force of magnitude QE, but because my charge is negative, it goes the other way. So that brings us to our first important point about electric fields. They tell us which way a positive charge would move if it feels that electric field, WWPD. What would a proton do, or what would a positive charge do? So sometimes I will ask you that question, WWPD, as a way to remind us that electric fields tell us, well, this electric field's to the right, positive charges to the right. It also tells us how much force we get for a certain charge Q. So if I want, if I do Q times E, I get my force. And its units, well, if I rearrange this, F over Q, that is newtons per coulomb. So it literally tells me for a certain number of coulombs of charge, how many newtons of force do I get? So again, if I want to know how a charge will move and what force it will feel, I have to find my electric field. So let's look at a little example here. We've got an electron that's entering a region of space that has a uniform electric field of 212 newtons per coulomb, directed upward as shown. So we want to know what's the acceleration experienced by the electron, and then we'll deal with part B in a moment. Well, notice the diagram kind of suggests that the electron gets pulled downward even though the electric field is upwards, because remember, electrons are negative. The electric field tells us what a positive charge would do. The positive charge would move up. So an electron, cheeky little thing that it is, wants to get pulled, wants to be contrary and wants to get pulled down. Well, if I want the acceleration, of course I know. How do I find acceleration? I use F equals ma. But I also know that the force that it feels will be equal to Q times E. So if I calculate Q times E, the force that it feels is, let's see, 1.602 times 10 to the negative 19th. And now if you're screaming at me that it's negative, we are looking for the magnitude of the force here. Be careful with that in here, because we've got positives and negatives floating all around. So it always calculate the magnitudes of forces and then use your intuition to figure out whether they're up or down. Times, let's see, the electric field is 212 newtons per coulomb for a grand total of 3 point, I'll just round off here, 3.4 times 10 to the negative 17th newtons, a very tiny force. But if I find my acceleration, which is that divided by mass, if I go ahead and divide by the mass, which is 9.11 times 10 to the negative 31, a very small mass, I get 3.73 times 10 to the 13th meters per second squared, which is equivalent to about 3.7 trillion Gs of acceleration. So I get a tiny little force and a massive acceleration because the mass of the electron is so tiny. A couple quick notes. You will notice that if I kind of do this F equals ma, F equals QE thing and solve for A, I get this little Q over M in my acceleration, which is called the charge to mass ratio. It's the ratio of charge to mass. And this comes up an awful lot in these kinds of problems where we're interested in how a particle moves. If I send two particles through with the same charge but different masses, like if I sent through a muon, which has the same charge as an electron but much more mass, it would be deflected less because it's going to feel the same force because of its charge, but it will accelerate less. So this charge to mass ratio does come up. Also, as to the second question, do we need to consider gravity? Well, gravity is going to provide the electron with an acceleration of 1 g versus 3.7 trillion Gs. So the answer is generally no. We don't need to consider gravity unless specifically directed. So if there's a question that requires gravity, suggested. If there's a problem that requires gravity, then we'll use gravity. If there's a problem that doesn't require gravity, we'll typically pretend that these things are ignoring gravity because gravity is such a tiny, 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 tiny little force compared to electrostatic forces. All right. Testing. Sorry, I apologize. My mic turned off. But what happens if I don't know the electric field yet, right? So let's say I've got these two charges sitting alone in space, a positive and a negative charge. I know, because I told myself this a moment ago, that they should attract each other. They should experience some force that will pull them together. What the heck force is it? I don't know what force that is. I should be able to figure it out, but I don't know what force it is. So let's see if I can figure that out. Well, remember F equals QE, right? So let's say let's call this one Q1, and we'll call this other one Q2, right? Well, let's say, what if I could figure out the electric field that Q1 puts out? So maybe Q1 puts out some kind of electric field. If I can figure out what electric field it puts out, then I can say, well, Q2 feels that electric field, and it will feel some force equal to Q2 times the electric field from Q1, and I should be able to calculate this force. So let's see if I can do that. It turns out that I can. So the electric field for one charge, here it is for a positive charge, is given by this equation. E equals and the E vector, is has a magnitude of 1 over 4 pi epsilon naught times q over r squared. Now notice this little r hat here, that's just a direction. It doesn't have any, it's not an actual r, so it's q over r squared. So a couple things to notice about this. First of all, it is an inverse square law, just like gravity. So you get twice as far away from this charge, the electric field gets 4 times weaker. The more charge you have, just like gravity, like with mass, the stronger an electric field you get. So if I have 2q, my electric field gets twice as strong. It is a beautiful radial symmetry. It is actually in 3D. And there's this new constant out front. Instead of like big G for gravity or whatever, we have 1 over 4 pi. You know what 4 pi is. And epsilon naught is this new constant, which is called the permittivity of free space, which is just this universal constant of the universe, which tells us how easy it is for electric fields to spread through a vacuum. And this constant has a value, 1 over 4 pi epsilon naught. It's sometimes called K, the Coulomb constant, of 8.99, about 9 times 10 to the ninth. Notice times 10 to the ninth, when we did gravity, we had 10 to the negative 11th, again, reinforcing that electrostatics is much, much stronger than gravity. Notice also that my electric field for a positive charge points out everywhere. It always points away from the positive charge. Because remember, an electric field it communicates forces to other charges. And it specifically tells a positive charge what it should do. Well, this is a positive charge in here. What does it want to communicate to another positive charge? It wants to communicate, get away from me. It wants to communicate, go away. So this electric field points out everywhere. So if I put a second positive charge, it's going to feel a force pushing it away. So the electric field of a positive charge pushes out everywhere. The electric field of a negative charge, similarly, is in everywhere, because if I put a positive charge over here, it should get attracted. It should follow those field lines in. Similarly, if I put a negative charge, it should do the contrary thing and go away. So we have these electric field lines that always go out from positive charges and point in towards negative charges. And it's still that same equation, 1 over 4 pi epsilon naught q over r squared. So let's see if we can calculate this. Let's practice with this, and then we'll go back to our original question. So let's see if we can find the E field at the origin here. And you might look at this and say, but Mr. Bates, there's nothing at the origin. How can I find the electric field? There's nothing there. Well, that's the thing about fields that makes fields so useful, right? Is there doesn't have to be anything there for there to be an electric field there. In the same way that I can point to a spot in space and say, well, there's a gravitational field here, right? If I put something there, it'll fall. Gravity's still there, even if it's not actively pulling on anything. So we can still find the electric field at the origin. And if we do that, we're going to have to do that because by considering the contributions of all of our different forces. So we're going to go, the electric field here is 1 over 4 pi epsilon naught q over r squared. Let's remind ourselves of that. All right, so if we're sitting here at the origin, what's influencing us? What's providing an electric field? Well, our plus 4q is going to provide an electric field. And so what's the contribution of the electric field over here? Well, remember, for a positive charge, that electric field points out everywhere. So if I'm over here at the origin, that electric field vector is going to point straight away from it. So we'll call this E1. Point straight away from it. It's trying to push that point away. Similarly, we're going to get something here. We'll call this 2. For a negative charge, it's going to point straight this way. And for this negative charge, it's going to point actually in as well. So we're going to get E2 and E3. Remember, electric fields for positive charges point away from that charge. Electric fields for negative charges always point towards that charge. So I've got 3 different vectors. How can I find the total electric field vector? Well, by adding them up. So let's go ahead and calculate all my little things here. I've got 2 that are in the same direction here, so let's see if I can find those. So E1 will be 1 over 4 pi epsilon naught. Its q is 4q over, okay, the radius is, let's see, looks like 1, 2, 3. So 3 squared is 9, okay? So that's what I get from E1, 4q over 9. For E1, we'll calculate E3 just to have the same one in the same direction. We get 1 over 4 pi epsilon naught Q over 1, 2, 3, also 9. Notice I'm not making E3 negative because I ultimately want to add these two up. They're pointing in the same direction. And so I don't want to confuse myself about which way things are pointing. This is the magnitude of the electric field. Magnitudes are always positive. And I'm going to use my vectors and my intuition about which way things point to decide whether to add or subtract them. Last but not least, I have to go calculate E2. So 1 over, similarly, 4 pi epsilon naught. I've got, let's see, 1, 2, 3 again. So over here, I've still got Q over 9. All right, so now I get to add these up. In the x direction, I've got two vectors. I've got E3 plus, well, I meant to draw E1 as the long one, so let me swap those. I've got E3 plus E1. And in the y direction, I have just E2. So if I want to find the magnitude of my total electric field vector, I've got to do a little bit of Pythagoras. So the magnitude of E total will be, let's see, well, so the 1 over 4 pi epsilon naught is just going to be part of all of them. And I guess so will the Q. So then I have the square root of, let's see, 4/9, but I have to square them because this is, you know, a squared plus b squared. So let's see, I've got 4/9 plus 1/9 in the x direction gives me 5/9. So I get 25 over 81 plus in my up direction, my y direction, I just get 1 over 81. So again, this is some Pythagorean theorem action. So I get, what do I get? I get Q over 4 pi epsilon naught. So it's root 26 over 81, which is, I guess, root 26 over 9. So not the world's most intuitively satisfying answer, but I can just do a little bit of vector math to figure out what they are. So my net thing points this way because it's getting pushed. My electric field vector is to the right from my positive charge, and for my two negative charges, I get contributions to the right and up. So that's my total electric field at the origin. And what's nice about that is if I take a new charge out of my pocket and bloop, place it down here and call that, you know, little q, I could immediately calculate the force that little q is going to feel, because it'll feel a force little q, its own charge times, you know, this total electric field that I found. Okay. So let's try to put this together and figure out what this force should be. So I'm going to go ahead and consider. Let's look at the force between these this way. So I'm going to say, what if I'm going to sit here as Q2, and I'm going to put out an electric field. My electric field points outwards in all directions, right? So if I'm over here where Q1 is, the electric field from Q2 points this way. I'm going to call that E2 for the electric field on Q, the electric field from Q2. So what does Q1 feel? Q1 feels a force, F on 1, which is equal to, that's kind of a terrible color. Let's, sorry, my mic keeps cutting out, I don't know why. So let's try this color. So F1, the force on Q1, it's going to feel this force, which is equal to Q1 times the electric field that it feels. It feels the electric field of Q2. Note, particles never feel their own electric fields, only the electric fields of other things. So, well, I know what E2 is, because I happen to know that that's 1 over 4 pi epsilon 0 times Q2 over, well, let's call the distance between them R. So we'll call the distance R. So what I get here is I get I can move that Q1 inside, 1 over 4 pi epsilon naught Q1 Q2 over R squared. But wait. Who's to say that Q1 feels the electric field of 2? What if I do it the other way? What if it's Q1 that's putting out its own electric field and it's Q2 that's feeling it? So let's try that, right? Well, that's easy enough. I know that that the force that Q2 is going to feel is going to be Q2 times the electric field from 1. So that's Q2 times, let's see, 1 over 4 pi epsilon naught. Well, the electric field from Q1, I happen to know, is just going to be Q1 over r squared. So I get a totally different answer of 1 over 4 pi epsilon naught Q1 Q2 over r squared. Oh, they're the same. They're the same. What about the directions? Okay, well, charge 2 sees an electric field that points inwards, and being a positive charge, it follows it inwards. Q1 sees an electric field that's pointing away, but being a negative charge, it's contrary. And it goes, okay, so I end up with forces in the same direction. They're both inwards and of the same magnitude. And this is a very special little case of this electric field law, which I would love to be able to show you, which is that the force between these two particles is K, and again, that big K constant is 1 over 4 pi epsilon naught, Q1, Q2 over r squared. So just like with gravity, actually very, very similar to gravity, we end up with this law that some constant times Q1, Q2, or two things, divided by r squared. And this is something called Coulomb's law. Coulomb's law. And this is only used for calculating forces between two charges, right? Remember, in general, F equals QE, but under certain circumstances, when we have just two charges, it's much easier to calculate it as using Coulomb's law. So if I have two charges here, like a plus 4 Coulomb and a negative 2 Coulomb charge that are half a meter away, I could calculate that force, 1 over 4 pi epsilon naught times Q1 is 4 coulombs. Q2 is, now I want to be careful here. It says negative 2 coulombs, but notice the absolute value signs, 2 coulombs over 0.5 squared. So if I go ahead and calculate that out, I'm going to get a very big number. Why did I use 2 coulombs instead of negative 2 coulombs? Well, because remember, the magnitude of our force only depends on the amount of charge. It's much easier for me to calculate the magnitude and then be like, oh, look, it's positive and negative charge they're going to attract. Otherwise, you risk from Coulomb's law getting negative signs and then accidentally like adding with negatives and subtracting when you don't mean to and all kinds of things. So our force here is a whopping 2.88 times 10 to the 11th newtons, which is just an astronomical amount of force. Because again, a Coulomb of charge is, to use a technical phrase, a butt ton of charge. So reminder, charges never feel their own electric field. They only feel the electric field of other charges. Okay. So what if it's a more complicated arrangement? So how would I figure out the net force on this middle charge? Well, I'd have to do all of the vector stuff, right? Well, this middle charge is going to get attracted to this one and attracted to this one, although not as strongly because this one's further away. It'll get repelled from this one, and it'll get repelled quite strongly from this one because it's strong. And then I have to go calculate all of those, do a little vector math, add them all up, figure out which way things are pointing. So in general, if I want to figure out the force on something, it's the same way for anything else. I draw a free body diagram, calculate all the things, and use my vector math and Pythagoras and all those things to add it up. So let's practice. Let's go back to the same diagram, but instead of asking about the electric field in the middle, we're actually going to try to find the force on the top charge due to the other two. So let's go ahead and look at this using Coulomb's law, right? So what's the interaction going to be between our plus 4 and our minus q? Well, it's going to get attracted this way. So again, if we go 1, 2, 3, we'll call this the F 1 on 2. So it's the force of 1 on 2. Well, 2 and 3 are going to repel, so this one's going to be pushed this way with a force F 3 on 2. And I want to quickly note that these two forces are going to be at perfect right angles to each other because of the nature of our scenario, which actually helps us quite a lot. So yeah, so let's see if we can figure this out. So F1 on 2, right? F1 on 2 is going to have a strength of 1 over 4 pi epsilon naught. I have to take the product of the two charges. Now remember, even though this one is negative, we're just going to treat it as positive for calculating the magnitude of the force. We're going to use our vectory knowledge of what the things do to figure out which way it points. So I get 4q squared over, Well, now I need to figure out how far apart they are. What's the radius here? So if I look, let's see, this is 3 and this is 3. So I can do a little bit of math and find that the radius there is 3 root 2. And so when I square it in my equation, I get, let's see, 9 times 4. No, 9 times 2, excuse me. I get 18. I get 18 there. F2 on, oh, sorry, getting my subscripts wrong. F3 on 2 is 1 over 4 pi epsilon naught. It's also has a radius of 3 root 2 because it's also nice and symmetric, but this is only q squared because it's negative q and negative q. So now if I want to figure out the magnitude of the total force, well, I can do a little bit of the Pythagorean theorem. I can do a little bit of the Pythagorean theorem here. So I'm going to get 1 over 4 pi epsilon naught on the outside, and I'm just going to be a little bit more careful than I was before. So I'll get 16q to the 4th over whatever 18 squared is, plus q to the 4th over whatever 18 squared is. So I'm going to get 17q to the 4th over 18 squared, which is to say I'm going to get q squared over, let's see, 18 times 4 is 52. Yeah. These buttons are so clicky. 72, right? I can do that. 72 pi epsilon naught times whatever the square root of 17 is. So in this case, I just want to note one of my forces is 4 times as big as the other because the distances are the same. So what I've really got is I've got kind of 1, 2, 3. I've got kind of like a big vector this way and a vector a quarter its length that way. So my total force on the thing is going to be like that way. It's going to be substantially more towards the 4q side because it's so much stronger. But still, we can calculate it and find the force just using vector stuff. So to summarize, each individual charge produces an electric field with this strength, right? So if I have one charge sitting in space, I know that it's electric field, which points outward if it's a positive charge, and inward if it's a negative charge. Has a strength of 1 over 4 pi epsilon naught q over r squared. So the further away I go from the charge, the weaker and weaker its individual electric field gets. Now, if I have a more complicated arrangement of charges, my field, as you can kind of see from this diagram, gets more complicated. So this equation really is only valid for particular individual charges. Charges in electric fields, if they're experiencing an electric field, they feel a force equal to q times that electric field. And in the special case where I just have 2 charges, or like 3 or 4, and can kind of do all the math myself, I can combine those 2 equations to figure out Coulomb's law that the force between them is 1 over 4 pi epsilon naught q1 q2 over r squared. So there's a lot of different things that I can do here. If I need to find the electric field, I've got this. If I already have the electric field, I have this. And if I just have 2 charges, I can kind of short circuit finding the electric field and doing this. The last thing that I want us to leave with is this question. And of course, my mic cuts out at the very last minute. The question that I want to leave you with is, how do I know that this is the field for one charge? Where did this come from, 1 over 4 pi epsilon naught q over r squared? And can I calculate the electric field for a more complicated arrangement of charges? And the answer is, yes, you can, to the second question. And for the first one well, actually, I guess the answer to both questions is the same, which is the next thing we're going to study, which is called Gauss's law. So I look forward to doing Gauss's law with you. All right, thank you.